Speedier than the outer layer of space-time, it can stay aware of it, and it'll essentially tear. I'm frightened by this at this point. Our night sky is evolving quickly, and in a matter of various years, while conceivably not sooner, it may turn out to be totally unrecognizable. Cosmologists, for the most part, are sounding the alarm. Specialists like Neil deGrasse Tyson have actually affirmed the inevitable effect of Polaris, and the story behind it is very astounding. Polaris, known as the North Star, has for quite a while been a constant in our night sky, filling in as a dire reference point for stargazers, navigators, and space experts. This could soon change, adjusting our night sky and astronomical evaluations. We ought to plunge into the significance of this danger and its suggestions for all of us. Join us as we uncover the narrative of Polaris as it gravitates toward its end. For quite a while, Polaris has guided sailors and stargazers alike, standing firm on a remarkable position as a guiding light. Its decided presence in the night sky has been fundamental for navigation. Anyway, this stability may soon be disturbed. In September 2023, an investigation paper presented by the regarded Royal Astronomical Society cast doubt on the destiny of this sublime light. Polaris is near the unstable edge of detonating, possibly dispersing from the evening sky forever. Before we investigate the outcomes of this openness, we should get more familiar with Polaris. Known as the North Star or Pole Star, Polaris is extraordinary due to its closeness to the celestial North Pole. Arranged straight over Earth's North Pole, it shows up nearly fixed in the northern sky and is situated in the constellation Ursa Minor, or the Little Dipper. Polaris sparkles as a reasonably staggering yellow-white giant star, a part bigger and more brilliant than our Sun. It's not a single star. Anyway, it's part of an intricate triple star system, with Polaris A and Polaris B forming a binary pair, while Polaris B orbits them. The connections between these stars make gravitational forces that shape their orbits and influence their behavior. Any disturbances in these connections can lead to unpredictable variations in the star's brightness or pulsation patterns. However, the particular components behind these interactions remain tangled. Polaris is situated around 323 light-years from Earth, meaning the light we see from it today began its journey a long time ago. Therefore, if Polaris were to somehow detonate now, we wouldn't see it until more than 300 years later. It's even possible that Polaris has already detonated, and we are yet to see the light from that event. Since forever ago, the North Star has held significant social, navigational, and symbolic importance. Its unfaltering quality and fixed position made it a vital guide for ancient mariners, helping them navigate across oceans and lands. Symbolically, Polaris represented relentlessness and course, remaining immovable amid the ever-changing night sky. For astronomers, Polaris has served as a critical reference point, aiding in the study of celestial movements and variable stars. As a Cepheid variable star, its periodic variations in brightness have provided essential insights into celestial properties and the nature of variable stars. This characteristic also played an essential role in determining astronomical distances and calibrating instruments. These pulsations follow a predicted pattern, which has been a standard for the star, making it easier for us to anticipate its behavior. However, as of late, Polaris has wandered from this standard behavior. This irregularity in its pulsation cycle has confounded astronomers, prompting a closer examination of this curious anomaly. As opposed to following its expected pattern, Polaris has begun showing unpredictable patterns of dimming, raising concerns among scientists that the star might be approaching the end of its life. This aligns with behaviors typically seen in stars approaching the end of their life cycles. The steady evolution of Polaris's pulsation period, which was once consistent, can be attributed to interactions within its star system. We've seen an annual increase in the pulsation length of 4.5 seconds, which may seem minor, but it holds significant implications. Some astronomers suggest that gravitational interactions between the Polaris stars could be causing these changes in its atmospheric conditions, directly influencing its pulsation patterns. Others are more concerned that it is nearing the critical edge of detonating. The similarities between Polaris's behavior and that of Betelgeuse, another notable star in the Orion constellation, are striking. Both stars have exhibited complex irregularities in their brightness, raising concerns about a potential explosion as stars in their twilight state often show such irregularities before reaching the end of their life cycles. NASA has expressed increased concern about Betelgeuse. However, formal attention has not yet been directed toward Polaris. As a Cepheid star approaches the end of its life cycle, it undergoes several phases, including the primary stage, the red giant stage, and finally, the supernova explosion. Considering Polaris's sporadic pulsations, researchers predict it has entered the stages of helium exhaustion, typical of giant stars approaching their end. These abnormalities in Polaris's behavior align with patterns characteristic of stars in their twilight stages. However, convincing signs of its impending supernova remain unclear. Astronomers are continuously monitoring these anomalies to understand Polaris's fate. If Polaris somehow undergoes a supernova explosion, it would likely be a massive event in our sky, potentially eclipsing the Moon and becoming one of the brightest objects visible for days, weeks, or even months. Its appearance could dramatically alter our perspective on notable star groups like the Big Dipper or Ursa Major, of which Polaris is a part. Rest assured, Earth would almost certainly be completely safe, regardless of whether Polaris were to explode, given its mass and distance from us. While a Polaris explosion may not be as visually stunning as Betelgeuse's, it could still be visible to the naked eye for an extended period, surpassing nearby stars. Astronomers and observatories would undoubtedly take notice, sparking interest within the academic community and among stargazers. However, the effect on Earth's climate or ecological systems would be less significant compared to a closer supernova event. But what about Polaris itself? What will be its fate after a potential supernova event? We should clarify one thing. While giant stars commonly end their lives with a supernova explosion, this is unlikely to be the case with Polaris. When a massive star goes supernova, a tremendous explosion occurs within it, marking the final, devastating stage of its life. This process involves a complete collapse of the core, triggering a violent shockwave that causes the star to explode. However, Polaris is not massive enough to undergo such an explosion. Instead, when Polaris exhausts its nuclear fuel, it will shed its outer layers and transform into a white dwarf. This transition will not result in a supernova, but rather a peaceful end as it evolves into a small, very dense celestial remnant. A white dwarf is the remaining core of a low or medium-mass star that has depleted its nuclear fuel. It's incredibly dense, about the size of Earth but as massive as the Sun. When this happens, we will no longer see its remnants from our planet. Like SN 2011 Fe or SN 2014 J, they give fundamental information for understanding the potential results of the Polaris blast. For instance, SN 1354 prompted the creation of the Crab Cloud, a cloud that proceeds to grow and create radiation across different frequencies, offering cosmologists a rich field for concentration. Additionally, SN 1987A, seen in the huge Magellanic Cloud, gave insights into the processes of nucleosynthesis and the mechanisms of cosmic explosion remnants, including peculiarities such as the formation of nebulae, the release of colossal beams, and changes in shine, which can reveal insight into Polaris' extraordinary qualities. The development of nebulae, like the Crab Cloud, results from the release of material during the cosmic explosion blast, which then interacts with surrounding interstellar gas and dust, enhancing it with heavy elements and contributing to the cycle of celestial birth and death. Furthermore, the release of massive beams and high-energy particles, quickly moved by cosmic explosion shock waves, has implications for astrophysical cycles and galactic radiation conditions. To make a conclusive comparison, researchers are assessing differences in the large-scale creation and speed of ejected materials between the predicted Polaris blast and other observed events. This includes concentrating on the light curves, spectra, and remnants of these events, and extrapolating similar attributes for Polaris' anticipated blast, evaluating whether it might lead to the formation of nebulae or massive galactic dispersions. This helps improve our understanding of its potential outcomes. Another significant area of study involves examining the pulsational instability of stars moving toward their end stages, comparing Polaris against other cosmic explosion ancestors. This general investigation can assist in estimating similarities or deviations, and also provide insights into the explosive nature. Pulsational variability in stars approaching the end of their lives might be indicative of internal hazards or impending catastrophic events, offering signs to the developmental processes leading to cosmic explosion blasts. Despite careful observations and extensive research, space specialists remain perplexed by the anomalies found in Polaris behavior. Unraveling the unique circumstances driving these abnormalities holds the key to advancing our understanding of celestial evolution. Grasping the factors responsible for Polaris' inconsistent throbs requires interdisciplinary collaboration, as well as the development of cutting-edge theoretical models and observational methods. The potential loss of Polaris as a major reference point in the night sky raises key questions for cosmic studies. Ground-based telescopes and astronomical measurements would require recalibration, influencing the accuracy of vast assessments. The absence of Polaris could also affect navigation systems and cultural practices based on celestial milestones, highlighting the significance of this astronomical event. The mysterious behavior displayed by Polaris emphasizes the need for deeper investigations and dedicated research efforts. Cosmologists must grapple with the complexities surrounding its sporadic throbs and provide significant insights, recognizing the importance of advancing our understanding of divine intricacies. The answer to Polaris' fate remains uncertain, and only time will reveal its true nature. Still, the quest for knowledge and understanding, in the face of immense uncertainty, is a testament to humanity's enduring interest in unraveling the mysteries of the universe. The implications of Polaris' potential downfall stretch beyond mere galactic curiosity. They address the very fabric of how humankind perceives its place in the universe. Since the dawn of time, celestial bodies have served as markers of time and navigation, guiding pioneers across uncharted waters and lands. The absence of Polaris wouldn't just disrupt traditional navigation methods. It could also have sweeping implications for cultural legends and imagery associated with the North Star. In various cultures, Polaris has been key to myths and spirituality. For example, Native American tribes often saw Polaris as a guiding light in their stories, representing hope and determination. Similarly, the ancient Egyptians used the North Star in their architectural designs, aligning pyramids with its position. The disappearance of such a prominent star could alter cultural narratives and the structure of human experience related to navigation and direction. Moreover, the academic community stands to face significant challenges if Polaris were to disappear. Cosmic measurements and observations heavily depend on established reference points. Polaris' role as a consistent guide has facilitated the alignment of instruments and models used to study distant galaxies, star developments, and even the expansion of the universe. The sudden absence of Polaris would require recalibrating many of these systems, potentially leading to discrepancies in measurements and understandings of celestial phenomena. As astronomers shift their focus to observing Polaris more closely, new observational advancements are being developed. Progress in spectroscopy and photometry enables researchers to analyze light emitted by stars in extraordinary detail. These tools help identify minute changes in brightness, which are crucial for understanding the mechanisms driving celestial behavior. As scientists gather more data, they aim to refine their models of stellar evolution, especially regarding stars in the later stages of their life cycles. The study of other similar stars, such as Cepheids and red giants, offers insights that could prove valuable. For instance, astronomers are studying factors like the period-luminosity relationship, which supports estimating distances across the universe. By comparing these stars' behaviors with those of Polaris, scientists hope to gain a clearer understanding of celestial dynamics and evolution, further enhancing their interest in the design of our universe. In addition, as the search for exoplanets intensifies, the study of Polaris and its companions becomes increasingly important. Understanding the characteristics of stars in triple systems can provide valuable insights into the formation and habitability of planets orbiting them. Astronomers are keenly interested in how such stars influence their surroundings, potentially impacting the conditions under which planets form and evolve.